Great. Okay. So let's start. So in week 3, okay, so till now what we have done. Basically from week 1 to 4, you have unsupervised learning. In week 1, you have in week 1 and 2, you have representation learning, in which in week 1 we have covered PCA, and in week 2 we have covered kernel PCA. Now we are on week 3. So in week 3 we have clustering, and in week 4 we have estimation, GMM, and EM algorithm. So discussion for today is clustering. So let's start our discussion. Let's say this is our data set. This is the type of data we have. All these blue points represent the data points. Well, when we run PC on this data, we'll get the direction in which data has most of the variance. Okay. After that, what we'll do, we will have proxy points. That is, we will have new points representing the original data set. Okay. But there is something else in this data which PC is not able to capture. As you can see in the data is forming clusters. This is one cluster, this is other, this is third cluster. Well, our PC is not able to capture this cluster, correct? It is only able to capture the direction in which we have most variance. Well, the PC1 does that. Okay. So now what's our goal? Our goal is to develop an algorithm that is able to understand, or that is able to capture this cluster, these clusters. Okay. So is it clear? Hello. So is the idea clear here? Okay. Now let's move ahead. So this is what we have written here. On using PCA, here we capture the direction that captures most of the variance. Well, apart from the low dimensional linear subspace, well, this line is the low dimensional linear subspace in which your data set lives. Data set has clusters which PC is not able to capture. Okay, so we want to develop such an algorithm. Okay, so we want to develop an algorithm which captures or understands these clusters. Okay, that is, let's say we are given data set. Okay, we want to partition the data into k different clusters. For example, well, just give me a second. Yeah. Well, for example, there can be multiple ways of clustering this data, right? So let's say we have chosen k is equal to 3. So for k is equal to 3, one possible clustering is, well, you have x1, x2, x3 in one cluster, then you have x5 in another cluster, and x4 in the other cluster. This is one possible cluster. And let's say, well, the data set here is, and the data set is this x1 to x5. So this is one possible way. The other possible way is, let's say you have x1, x4 in one cluster, x2 in another cluster, and x3, x5 in the third cluster. Well, there can be a lot of ways, right? So total number of possible ways are 3 raised to the power 5. And how's that? Because each point has three options: cluster 1, cluster 2, or cluster 3. And in total, how many points we have? We have 5 points. So 3 into 3 into 3 into 3 into 3. Well, this is the number of possibilities you have. So is this clear? Hello, is this clear? Now,
Yes.
okay, thanks. So now let's move ahead. So what's our goal now? We know that we want to partition our data set into some K clusters. So what now? Well, we'll have different types of clusters, right? Different ways of clustering. So we want to understand what is a good performance measure for a for particular data set, right? So if we have, well, this is your clustering method. This is your clustering way. You want to understand how good is this clustering. Well, is this one better way or this one better way? We want to understand that. Okay, what is a good performance measure for partitioning data into clusters? So let's say this is your data point, and corresponding to each point you have cluster indicator, that is corresponding to x1 you have z1, and z1 will be equal to the cluster where your x1 belongs. That is, if x1 belongs to cluster 2, then the value of z1 will be equal to 2, and so on. Okay, so this is cluster indicator. And now what's our question? Well, given a cluster assignment, well, this is one cluster assignment, this is another cluster assignment. So given a cluster assignment, we want to understand how good is the assignment. Okay, so well, what is a good assignment? That's the question now. Okay, so okay, so in a way, cluster belonging to points belonging to a given cluster, let's say points belonging to cluster 1, they will be similar to each other, right? That's why they belong to a given cluster. Whereas points belonging to cluster 2 will be similar to each other, and the points of cluster 1 will be different to points of cluster 2. So, what's a good cluster? A good cluster should ensure that points within same cluster are similar while keeping different cluster well separated. Okay, this is the core idea. So, based on this, we can come up with a objective function. Okay, and this concept of a good clustering is called homogeneity. Okay, is this clear? Hello.
Yes.
Okay. Now let's move ahead. So now the goal has changed, right? So we know that, okay, well, if points belong to if points belong to same cluster, then they will be similar to each other. And when can you say that two points are similar to each other? You can say that when the distance between 2 points is less, right? Well, when you are comparing, let's say, uh, these are points of one cluster and these are points of other cluster. Okay, so these 2 points will be similar, but the points of different cluster will be different. Okay, so this means that the distance between points of same cluster will be smaller compared to difference between, by difference I mean the distance between points of different cluster. Well, okay. So now there must be a cluster representative. Well, you will have a lot of points inside a cluster. This is one cluster, this is another cluster. So there will be there can be a representative, right, of a given cluster. So cluster 1, cluster 2. So a good representative for each cluster is its mean. Okay. So this means, well, for points belonging to same cluster, well, let's say we are talking about this point belonging to cluster 1. So the distance between the point and mean of its cluster will be less than distance between the point and mean of other cluster. So is this idea clear? Hello? Hello?
Yes.
Okay, let's quantify this. Okay. So how can we quantify this? Well, it's not very complex. We have to come up with an objective function. So what is the good objective function? What's a good? So summation I from 1 to n, summing over all the points in data set. We are calculating the distance between point and mean of the cluster where your point belongs, where xi belongs. Okay. So if your xi point belongs to cluster zi, well, note that this is cluster indicator for xi, and this will take some value like 1, 2, depending on the cluster where this point belongs. So this is now your objective function. We want to minimize this. So is this clear? Hello? Why we have chosen this objective function, is this clear?
Yes.
And here what is this mu zi? Mu zi is equal to, well, this is mean of the particular cluster. So we can calculate the mean by summing points from I1 to n. Well, we'll not sum all the points, we'll only sum the points belonging to the given cluster. For that we'll use indicator function. So zi equal to k, and we'll divide this by the number of points belonging to that particular cluster, and that we'll get from summation I1 from I from 1 to n. And here again we'll use indicator function, because we don't want to count all the points in data set. We just want to count the points belonging to given cluster. So is this clear? Hello?
Yes, sir, it's clear.
So now what? So, well, this is the objective function in hand. But the problem here is that we can't find the minima of this. This objective function right here is this problem, objective, this optimization problem is NP hard problem. And let's discuss about that. So let's say we have data set of 1000 vectors and we want to partition them in 5 clusters. So in total, how many possible ways are there of clustering? We have, well, each point has 5 options. So 5 raised to the power 1000 ways. Well, the number is very large, and this data set we have taken is comparatively very small compared to the real world data set. So the number of ways of clustering shoots up very quickly. So finding the minima for this objective function is very difficult. So that's the problem right here. So is that clear? Hello?
Yes.
So now we came up with Lloyd's algorithm. So what we do in Lloyd's algorithm, we randomly initialize our cluster indicator. That is, we assign random cluster to each data point. Well, uh, for point x1, let's say we have given the assignment z1 equal to 1. For point x2, we have given assignment z2 equal to 2, or and so on. Okay, so initially we assign random cluster to each data point. Okay, after that what we do, until convergence, we'll perform these two steps. The first step is compute the mean. Okay. So, well, this is your data set. Now what we do, we we have given random assignment. Okay, let's say these are my blue points and these are my orange points. After that, we compute the mean. This is the mean of the data of blue points, and this is the mean of data of orange points. After that, what we will do now, we have calculated the mean. So let's go back to definition of good clustering. Okay. Well, if clustering is good, that means the distance between point and uh, mean of the cluster where your point belongs will be smaller compared to distance between point and mean of other clusters. So we'll check that. Now what we will do, we'll calculate distance of each point with mean of cluster 1, that is we'll calculate this distance, and we'll calculate this distance. If the distance of current assignment, that is if the distance this distance is smaller than this distance, then the point stays in the present cluster. Otherwise, sorry, well, otherwise what we will do, let's say we talk about this point. So the distance between the this point and the mean of the blue cluster is smaller compared to the distance between the point and mean of its current cluster. So for such points, we change the assignment. Okay. So after computing mean, we do the process of reassignment. Okay. And when do we reassign a point? When the distance between the point and mean of its current cluster is greater compared to distance of the point to mean of some other cluster. Okay. Is that clear? When do we reassign a point to a different cluster? Hello.
Yes. Yes, sir. Yes, sir.
Yes. So now what we do? Well, let's see this in action. Okay. So this is our data set. What we do, we have given random assignment. These are blue points and these are orange points. After that, what we did, we calculated the mean. Okay. And then after this, what we did, we computed the distance of all the points to current mean and mean of the other cluster. If the distance between point and current mean is smaller than the distance between point and the mean of other cluster, then that point stays in the cluster. Otherwise, it is assigned to the other cluster. Okay. So accordingly, the points will change the color. Okay, as you can see here, and this steps continue after. Again, what we did after the reassignment, we calculated mean. Again, we calculated the distance. Okay. And similarly, in this way, again your assignment will change, and in the end you will achieve a state where all the points are happy. That means the distance between point and the current mean is smallest compared to distance between point and mean of other clusters. Okay. So in the end, with this algorithm, we achieve state of convergence. So is the algorithm clear?
Yes, sir.
Well, now what? So there are a few questions regarding this algorithm. The first question is, well, will it converge? Here we have shown that it converges, but will it actually converge? Uh, are we sure that, let's say, some point which got assigned to blue cluster, after one iteration, it got assigned to orange cluster, will it not keep oscillating between the clusters? Okay. That's the question we have. So now we'll talk about convergence of the algorithm. So before discussing the proof of convergence, we have to keep in mind one important fact, that let's say You have x1 to xn. These are your data points. Okay. And the value of v that minimizes the function summation I from 1 to n norm square of distance between point xi and some vector v. The v that minimizes this objective function is nothing but mean of the data points. Okay. Well, you can check that. You just have to differentiate it with respect to v equated to 0 and you'll get the value of v. Okay. So is this fact clear to you all? Hello.
Can you repeat it, sir?
Okay. So let's say we have data set of n data points x1 to xn. Now we are talking about an objective function which is summation I from 1 to n, and we are calculating the distance between point xi and some vector v. Okay, we are calculating this distance for all the data points, and the vector v that minimizes this objective function is mean of the data set. Is that clear? Hello.
Yes, sir, got it.
Okay. Now let's dive into the proof of the convergence of the algorithm. So let's say we are at iteration t of Lloyd's algorithm. Okay, and the current assignment is this. Well, point x1 at tth iteration is in cluster, let's say, while point 2 at tth iteration is in cluster 3, and so on. We are at some assignment. Okay, this is the current assignment we are referring to, and this mu tk is what mean of the cluster k in iteration t. Okay, so after computing the mean, what we do, we update the assignment, right, as discussed here. And how do we update assignment? Anyone? Hello. Anyone? How do we update assignment after computing mean? Hello. Am I audible?
Yes, sir.
Yeah. Could you explain me how do we update assignment after computing mean? Anyone?
According to the distance.
Yes. We compute the for all the data points, we compute the distance between data point and mean of its current cluster, and the distance between data point and mean of other clusters. So if the mean of so if the distance between data point and mean of current cluster is larger compared to distance between point and mean of some other cluster, so we move the data point to other cluster. Is that clear?
Yes, sir.
Okay. So after reassignment, this is the uh, cluster indicator values. Okay. So now we'll talk about few values of objective function. So first of all, when we are at tth iteration, this tth iteration, so the objective function value at, well, we are talking about summation I from 1 to n, summation of norm square of xi, distance between xi, and mean of the current cluster where xi is assigned. Okay, so this is what this is the distance between data point and mean of its current cluster. Correct? Well, is this objective function clear? Is this function clear? What it is representing?
Yes, sir.
Okay. Now let's say, well, after that, what we do, we compute the distance between a data point and mean of current cluster, and distance between data point and mean of other cluster. So let's say this right here is what? This is summation I from 1 to n, distance between data point and the mean of the cluster where this data point wants to go. Okay, so is this clear? This is what this mu t zi t plus 1 is what? This is representing the mean of cluster where point xi wants to go. Okay, so is this function clear?
Yes.
So now tell me, what will be the relation between these two values? Will they be equal to each other, less than, greater than? What is the relation?
Uh, the left one will be less. Yeah.
Yes, the left one will be less. And why is that? Well, we are reassigning when the distance is less, right? So obviously, this value will be less. So is this clear?
Yes.
Now, well, this is value of objective function at intermediate stage. Okay.
Mm.
Now, after this, what we do? We accordingly reassign the points to clusters, correct?
Correct.
Depending on the cluster they want to go. Okay.
Mm.
So after reassignment, now we are calculating the distance between uh, each point and the mean of its new cluster. Well, this is what now we have entered in iteration t plus 1.
Mm.
Okay, and this is what? This is mean of the cluster where your point is present at this stage. Okay,
Okay.
so now what is the relation between these two? Well, we have just discussed before starting the proof that the minimizer of the function summation I from 1 to n, distance between point and some vector v, is what? Mean of the data points, right?
Correct.
And this is what? This is mean of the data points.
This one is.
Okay, so now this quantity will be less than equal to this quantity, correct?
Yes.
And in what case? Okay, well, we know it will be less than. So tell me in what case it will be less than equal to. In what case it will be equal to each other?
When it converges.
Yes, at the point, at the iteration of convergence. Well, let's say at tth iteration, all the points are happy. So after this at t plus 1 iteration, the values will not change, right? Because these two are same.
Okay.
Okay. So now we know that, okay, at iteration t, this is the value of objective function, and at iteration t plus 1, this is the value of objective function. Okay. So this quantity is less than something. Okay, let's say this is 1, this is 2. Let's say quantity 1, quantity 2, again quantity 2, and this is quantity 3. So here we have concluded that your 3 is less than equal to 2, which is less than 1. Correct?
Correct.
And 1 is what? This is the value of objective function at iteration t. And 3 is what? This is value of objective function at iteration t plus 1.
Yeah.
So this implies that objective function strictly reduces after each reassignment. Correct? And we also know that there are only finite number of assignment. Correct? From our argument here when we took an example. Correct? The total number of ways of assignment is finite. It is not infinite.
Okay.
So now what? Our value of our objective function is reducing after each iteration, and we know that there are only finite number of assignments. So this means that there are finite number of iteration. So eventually, what will happen? Your algorithm must converge. Correct?
Yes.
So now, is this clear? Why the algorithm converges?
Yes, I got it.
Now, let's talk about another thing, which is nature of clustering. Okay. So let's say we are partitioning our data set into two clusters, okay, with mean mu1 and mu2. After running the Lloyd's algorithm, we have achieved the correct clustering assignment, and means are mu1 and mu2. Okay. So for points assigned to cluster 1, what can we say? For points assigned to cluster 1, the distance between, let's say x, we have some point x belonging to cluster 1. So the distance between point and mean of cluster 1, where your point belongs, will be less than equal to distance between point and mean of the other cluster. Correct? Is this
Yes.
clear?
Yes, sir.
Now when we expand this, okay, just apply the formula of x minus y whole square. Just apply the formula. Okay, a few things will get cancelled, and in the end we'll get this inequality. So x transpose mu2 minus mu1, this will be less than equal to, what is this? This is difference between uh, distance of, well, sorry, this is difference between norm of mu1 and mu2 divided by 2. Okay. So now let's plot the line. Okay, first of all, let's replace inequality with equality and plot this line. Before that, what we can do? Well, we can conclude one thing, that this inequality is of the form x transpose w less than equal to b. Correct? This is of linear form. Correct?
Yes.
So now what? Let's plot the equation x transpose mu2 minus mu1 equal to 0 on the graph. Okay, let's plot this line first of all. So your vector mu1 is here and mu2 is here. So the difference, mu2 minus mu1 will be here. Correct? And the magnitude of difference is this. Well, we can parallelly shift any vector. So this is the magnitude of difference. Correct?
Correct.
Now, well, this is the vector. So where will all x lie, where x transpose mu2 minus mu1 is equal to 0? Well, when we take dot product of two vectors, and dot product is 0, that means the vectors are perpendicular. Correct? So this means all the x are such that dot product of x with mu2 minus mu1 will lie on line perpendicular to this, and the line perpendicular to this is this green line. So now this is the equation: x transpose mu2 minus mu1 equal to 0. Correct? Is this clear?
Mm.
Yes.
Well, we don't want this equation, right? We want to get this inequality. So now what we'll do, we'll plot x transpose mu2 minus mu1 equal to this quantity. So we just have to parallelly shift this line, right? Because we are just introducing a scalar on the other side. Okay.
Mm.
So it will not pass through this origin. It will pass through. Well, its y-intercept will be what? Anyone? What will be the y-intercept? The value of b, right? Which is this. The magnitude will be this. Correct? Is that clear? Hello?
Um, can you explain once again, sir? Just
Okay. So, as I tell you
mm,
that when we talk about point, let's say y is equal to x. So it is here, correct? It passes through origin.
yeah,
Whereas when we talk about point y is equal to uh, x plus 2, what is the
yeah.
difference here?
It will move to point from the origin.
Yeah, it will be parallelly shifted, right? That's the
Yeah.
difference. And you can find that, right? Just put the value of y equal to 0. So what is the value of x?
Mm,
X will be equal to minus 2,
mm,
right? So it will be here, correct?
yeah.
The same thing is happening with this. So here what we have? Here we have x transpose mu2 minus mu1 equal to 0. Or you
Yes.
can say, yes, equal to 0. So we are just introducing what? Minus, this can be written as, uh,
Okay.
just a second. This can be written as x minus y minus 2, right? Equal to 0. So this is in the same form, right? So when we are
Yeah.
introducing a scalar and when we are moving it to left hand side and it is negative, so the scalar is this quantity. And when we move this entire quantity to left hand side, it will be negative, right?
Okay.
Okay. So we are just parallelly shifting this. Okay. That's it. Is that clear?
Yeah.
Okay. And now what is this other green line? This other green line is the equation x transpose mu2 minus mu1 equal to average of average of difference
Mm,
between norm of mu2 and mu1. Correct?
mm, mm,
So now let's say we want to talk about a point satisfying this equation. So a point satisfying this equation will be what? Mu1 plus mu2 by 2. And when we put this point in the equation, in the end, what we get the same thing. We get the right hand side value, correct? We will get this value. So this means that the average of difference, sorry, this means that this quantity mu uh, norm of mu2 minus mu1 by 2, this lies on the line. This will lie on the vector which represents the difference between mu1 and mu2, not this vector, the one which is parallelly shifted, this one. Okay, so the point satisfying it is here. This is
okay.
the point, and this point we are just labeling. So this point is what? This is mu1 plus mu2 by 2. Okay,
Mm,
so this means, well, given any clustering, what is Lloyd's algorithm doing? It is finding the half spaces which divides the cluster regions. So what it will do? It is trying to find mu's, that is mean, such that, well, after give a given mean, okay, mu1 and mu2, what we do? You find the distance between them. After that, the perpendicular bisector is the line separating the two regions. Okay, this is the main takeaway. That is, the perpendicular bisector of line joining heads of mu1, mu2 will be what? Will be the, you can say, the line dividing the clusters. Okay,
Okay.
is this clear? So
Yes.
when you have uh, k is equal to 3, in that case, what will happen? You will have three mu's, right? Mu1, mu2, and mu3. So what you will do? You will calculate
U1 plus
perpendicular.
U2 divided by 2. Yeah.
Yes, and in the end, you will get three different regions representing three different
Clusters.
cluster regions. Okay, this is region 1. Okay, so this is region 2. Okay, sorry. And the region 3 is this. This is region 3. So is this clear? What is
Yes.
the geometrical interpretation or nature of clustering?
Yes, sir.
Okay. Now the next part is the choice of K or the initialization. Okay. So first of all, let's talk about the initialization. Just a second. And one another important thing is that these regions are called Voronoi regions. Okay. So note, one important note here is that your cluster regions are intersection of half spaces. And what do we mean by half spaces? Well, any line, well, let's say we talk about this line. So this line divides your entire plane in two halves, right? Correct? Similarly, this line also, this divides your plane into two halves. And similarly for this line. So your cluster regions are intersection of half spaces are intersection of half spaces. Okay, and these regions these cluster regions are called Voronoi regions. Yeah. So is this part clear to you all?
Yes, sir.
Okay. So this was for nature of clusters. Now the next thing is your
One
initialization.
question.
Yes.
The Voronoi region is the intersection of two halves, no? So is the intersection is the perpendicular line?
Uh, yes. So let's look at that just a second. So when we say intersection of two half spaces, what do we mean by that? That's the question. So when we want to find the region of mu1, then what we do? We find the perpendicular bisector for this distance, this line. Okay,
Ah,
this is one half space, correct?
yes.
And then we find the perpendicular bisector for this. This is another half space. This
Okay.
is one half space. This is another half space. So the intersection of the two is what? Is your Voronoi region
Okay.
for cluster of mu1.
Okay.
Similarly, when we talk about mu2, we'll take this bisector. These are two half spaces, and this bisector. These are two
Okay.
half spaces. The intersection of the two will give you your Voronoi region.
Okay. Okay. Got it.
Okay. Now let's move on. Initialization. How do we initialize? That's the question now. Is anyone any doubt so far?
Shijit, I have one question. When we're initially calculating the distance of the means, right? Initialization, and we're seeing which cluster it will go to. If the distance is the same for both means, we will not move that point, right?
Yes,
If
will
it's in
not move.
cluster one, we will just retain it in cluster one.
Correct.
Okay, okay, thank you.
Now we'll talk about initialization. How do we initialize our clustering? Initialization. So one possible way is to, well, what we did in Lloyd's algorithm, we are assigning random cluster to data points. So here we'll not do that. What we'll do, we'll pick k means when we want to divide your data set in k clusters. What you do, you don't randomly assign points clusters. You choose k means. So from given the set of n data points, you pick you pick k points and you make them means of the cluster. Okay, so and this assignment is at uniformly random. Okay, uniformly random from the data set. So here, if you look carefully, well, uh, the image which I have taken right here. So first of all, what we are doing in the image actually, we are assigning cluster a mean. Okay, after that, depending on the mean, we are giving cluster to each point. Okay, and now as new points are added to the cluster, so the mean will change. So mean will be somewhere like here, let's say, and for this mean will be somewhere like here. So as new points are added to the cluster, depending upon their distance between the k means we have taken, the mean of the cluster will change. Okay. So now after that, what we do, we recompute the mean of the cluster and we again repeat the step. So is that clear? Hello.
Yes.
So actually what we are doing, we are choosing k means uniformly at random from data set. Okay. This is one method. And the other method which comes from
Sir,
k means,
If you say there are 10 data points, if K means two clusters, we are initializing from this 10 2 as mean of
Yes.
no? Yeah.
From the
Then
10
we
data
are
points, you are selecting
then
any
we
two.
are yeah, then we are calculating the distance from each of these mean to all other means all the data points. And wherever the distance is minimum, we are assigning these points to that clusters, respective clusters.
Correct. And this continues until convergence.
Okay.
And now, when we talk about the other method of initialization, which is coming from k means plus plus. So this is method of k means. When we talk about k means plus plus, what are we doing there? Well, instead of assigning random means, what you do, you choose first mean at random. Okay. So you choose first mean at random, uniformly at random, formally at random. Okay. And after that, you have set of data points, right? You are selecting any point from the set of data points and you are making it mu1 from x1 to xn. Okay. And after this, what you do for rest of the points, you will use a probabilistic way. So, tell me one thing. What is definition of good cluster? What are the characteristics of good cluster assignment? Anyone? We have discussed that already, right?
Sorry, can you repeat it?
What are the characteristics of good cluster assignment?
The distance should be minimum. I mean, it should satisfy the objective function.
That's not very accurate. So we discussed that uh, the distance of points of same cluster will be small compared to distance between points of different cluster, correct?
Yes,
So points belonging to a given cluster will be compact, okay? Whereas two different clusters will be well separated, correct?
Mm. Yeah, yeah.
So from this, it means that, well, let's say from given data set, let's say these are my data points, these are my data points, okay?
Mm. Mm.
If I have chosen
Mm.
this one as mu1,
Yes.
then mu2 will be
As per
should be far away from this, correct?
correct, correct, correct. Yeah.
So now what we will do, so first mean we have chosen at random. Now what we will do, we will give score to each point, we'll give some score to each point, okay? And let's say we are dividing our data set in small l clusters. So let's say this is the first cluster, and let's say this is the first cluster mean, and the second cluster mean is this. Now we want to find mu3. So for mu3, what you'll do, well, a point which is farthest from the two, will be a good candidate for mu3, right? So to all the data points, we will give some score. And what is the score? Well, we for all the data points, we calculate the distance between the data point and mu1 and data point and mu2. And the minimum distance of the two will be the score. So let's say this is 5 units and this is 12 units. So this right here, this point will have score 5.
Okay.
Okay. Whereas this point will have score equal to this distance because this distance is smaller compared to this distance. Okay.
Correct.
So each point will be given some score.
Mm.
Now these scores can be normalized such that uh, the point which has highest score uh, is normalized to score 1. Okay, so we are simply rescaling the scores in interval 0 to 1. Okay, that can be done in many ways, correct?
Mm.
Okay, so now this is what, well, as all the values are between 0 and 1, this is a probability density, right?
Yes.
Okay, so now the mu3 can be selected using this probability distribution. Okay, so the point which has highest minimum distance between point and mu1 mu2 will have highest probability of getting selected. That is, this point will have highest probability,
Okay.
whereas
Yes.
point like this will have minimum probability.
Mm.
Correct?
Correct.
So with this probabilistic way, we can select rest of the means. So is this idea clear?
Yeah.
Yes.
Yes, so I'll just simply write it that this this point has highest probability of being selected as mu3. Okay, and let me write the function for score. Okay, so the score for point x is what? Minimum distance between, well, what do you do for a given point? You calculate the distance of this point to all cluster means. Okay, so let's say we have cluster means 1 to L minus 1. L minus 1. So the smallest distance among these distances will be your score. So is this clear? So is this
Yes.
approach? Yes. So I'll just simply write one more thing that for L from, well, let's say we have taken mu1 and mu2. Okay. So for L equal to 3 to K, choice of mean, let's say some Lth mean is choice of this is probabilistically proportional to the score. Okay. Higher the score, higher the probability of the point being selected as mean. Okay. Probabilistic proportion. Is k means plus plus clear to you all?
Yes.
Okay, so tell me what's a possible drawback of this? Not a drawback, what's a uh, cost for this, you can say. The problem here is that it is computationally heavy compared to your simple k means. Why? Because at each iteration, what you are doing, you are calculating the score, correct?
Hmm.
So this involves more computation.
Okay.
Now the next point we want to discuss is choice of k. Well, in some problems, we may know the value of k already. Like when we talk about scores of student, okay, and we want to cluster them based on grades. So there are only certain grades we know. Okay, so in those cases, the value of k is known to us. But in other cases, the value of k may not be known to us. So how can we choose the value of k? That's the question. Okay. So let's see the objective function. Okay, for that, first of all. Okay, let me write the header first of all. Choice of k. Choice of k. So for the objective function to be minimum, and what is our objective function? The objective function is equal to summation I from 1 to n norm square of xi minus mu zi. Well, for this to be minimum, what is a good value of k?
N.
Well, if k is equal to n, in that case, it means that every point is a cluster in itself, which
Yes.
means that the cluster mean is equal to point. So when your data point or when all the data points are their own cluster, it means that the data point itself is the mean. So this quantity becomes zero. Okay. So for k is equal to n, the objective function is minimum. Okay. Well, but this is no good to us, right? What's the point of it then? Okay. So we want a small value of k because that will reduce the, sorry, uh, we want a smaller value of k, right? Because value close to n will do no benefit to us. Okay. So we want to get small values of k. So let's say, okay, when we talk about small value, what about k is equal to 1? Well, if you have k is equal to 1, in that case also, there is no benefit. Why? Because all the data points belong to a cluster only. Well, that makes no sense of clustering, right? Correct? Is that clear? Hello?
Yes, sir.
So, well, we want small value of k, but we also want to penalize the large values of k because, well, if you have very large value of k like k is equal to 1, in that case, the clustering makes no sense. And when you have very small value of k, which is like equal to 1, in that case also, you don't, it makes no sense of clustering. So we want k to be small. Okay, well, smaller the value of k, uh, the better the clustering, right? Well, if you have larger value of k, the objective function will be less, but the clustering will not be very good. So we want smaller value of k, and we also want to penalize, also want to large value of k. So we don't want very small value and we don't want very big values. Okay, so there is a trade-off. So now what can we do? So now the modified objective function for us, okay, when we talk about value of k, okay. So want to find k, we want to find k such that we have small value of small value of the below function. What is the function below? Well, your objective function, the original objective function value plus the penalty on k. Okay, we are imposing a penalty on k because we don't want very large value of k. Okay, so let's plot this. So when we plot this, plotting this, let's say this is our graph. The objective function, well, larger the value of k, smaller the, wait a second, is larger the value of k, smaller the objective function. So here you have k is equal to 0. Well, this axis is for k, and this axis is for function, objective function plus your penalty. Let's say just a second. This is what? The objective function plus penalty. Penalty. And x is for k. So larger the value of k, so smaller the value of objective function. So at k is equal to n, you'll have you'll have 0 value of objective function. Okay, and at k is equal to 0, sorry, at k is equal to 1, you'll have very high value of objective function. So the function will be like this. Just a second. Just a second. First of all, let me draw the graph. After that, we'll put the point. Okay, so just a second. Let's say this is the value of k equal to n. Okay, this is n. Okay, and this right here is equal to 1. Whereas your penalty will be small. Well, when your k is equal to 1, right? Because we are penalizing large value of k. And it will be very high when your k is equal to n, because we don't want large values of k.
Okay.
So the function for penalty will be like this. Okay, just a second. Somewhat like this. Okay, now the sum of the graph, which is objective function plus penalty of k, it will be somewhat like this. This function, this graph. This will be the graph of objective function plus penalty of k. So this value of k is the best value of k. Okay, because it is balancing between the value of objective function as and penalty. Okay, this is your k star. So is this clear?
Yes, sir.
Label the graphs. So objective function plus penalty. Penalty. This your green curve is what? This is for your objective function. Objective function, and this red curve is for your penalty function. Okay. So this was about your choice of k. So is this clear?
Yes.
Okay. So this was your week 3. Any doubt so far? Any doubt in week 3? Anyone? Any doubt? Is everything clear to you all? Hello?
Yes, sir, it's fine.
Okay, so I'll share the notes of the session in chat, and it will also be shared on calendar and mail. Okay. Mm. Next, we'll start with week 4 on Saturday, and we'll continue on Sunday. So Saturday, Sunday, we'll cover week 4, and after that, on next Wednesday, we'll do PYQs. So yeah, is that clear to you all?
Yeah. PYQ in the sense all days will be there, sir?
We have already covered PYQs of week 1, 2. Next, after covering week 4, we'll do PYQs of week 3, 4.
Okay.
Okay. If we have few more days before exam, okay, if we are able to
The
do all this.
PYQs of the previous, I couldn't attend week 1, PYQs of week 1 and week 2. If possible, that also, could you please paste
Yeah,
it on the group?
the video is on YouTube channel of Saranda House.
Okay.
Please take a look.
Okay.
Okay.
The one
Yes.
you posted
Yes.
in the chat.
Yeah. So that was it for the session. If you have doubt, please feel free to ask. Otherwise, we'll end the session.